We're going to do one more Simpson's paradox example so you guys can see why this wouldn't happen in a randomized controlled experiment. The last one we did was about the Berkeley graduate admissions. And see how it says right here, Simpson's paradox for observational studies. That's kind of your hint. It can only happen in observational studies. And what happens is, if you look at the overall results of a study, you see the opposite of the individual results. So let's look at our next example. This one we already did. It says, number 2, could smoking prolong life? And just reading this, could smoking prolong life? We all know smoking does not prolong your life. So this, if you see an article that has kind of a weird title, that might be, this is kind of a clue. Okay, I know this has got to be an observational study, and there's probably a confounder, because we know the opposite is actually true. So this is, again, just another example of Simpson's paradox. Okay, so let's see why. Let's look at our data. It says they did this 20-year study of British women, and they compared the death rates of smokers to non-smokers and found that, here's our results, 23% of the smokers had died compared to an even bigger number, 31.4% of the non-smokers. Strange, right? Could this be evidence that smoking helps you live longer? So right away, I know this is about smoking. It has to be an observational study, right? You can't assign people to smoke and people not to smoke. You're just observing what they naturally do. So with any observational study, I want to say maybe, I don't know, could this be evidence that smoking helps you live longer? Let's investigate. If it is, if there's a causal relationship, we're looking at our treatment is smoking, and then, yeah, so let's go ahead and write this. So our treatment is smoking, and our response is living longer. So we're seeing that people who smoke end up living longer. So if there is a causal relationship, there would be a causal link explaining what happens when you smoke. What about smoking cigarettes causes you to live longer? It'll be a direct relationship between this and this, treatment and the response. So this is if it's true, smoking does help you live longer. Or the more logical explanation is that there's a confounder. There's a third factor that we are not taking into account. So the confounder is going to be something that's associated with smoking and also associated with living longer. Okay, and another way to think of the confounder, it's a difference between the treatment and control group. So a difference between people who smoke and people who don't that is related to living longer. So what they did during this study, they said, all right, let's look at our data. Control for age. Maybe age is something that's affecting this study, right? Because if you're older, you're more likely to die. If you're younger, you're less likely to die. The probability goes down the younger you are. So what they did was they looked at the young people. So here's the young people. And so this is stratification, right? Controlling for age, dividing into subgroups based on age. The term we used the other day was called stratification. Same thing. That's how we check. Is age a confounder? Well, let's see. So it looks like the smokers have a death rate of 2.8%. Non-smokers, the death rate is basically the same, right? That difference is not significant. So non-smokers, they're basically saying non-smokers and smokers, if they're young, their death rate is low. That's what we saw. 35 to 64, that's probably the relevant age that we're interested in, because if we think about this, relevant age, the old people are probably going to have a high death rate, even if they smoke or not. And that's actually what we see. I'm going to look at that one first. So for anyone over 65, if you smoke, the death rate's 85.7%, and if you don't smoke, it's about the same, 85%. So our relevant age is the middle-aged people, just because smoking does take a while to have an effect on you. So if we look at the relevant age, we see that the smokers have a death rate of 26%, and the non-smokers have a death rate of 18.4%. So the smokers have a higher death rate for the middle-age group, the relevant age group that we're looking at. The paradox is the idea that if I look at the overall totals, the smokers actually have a lower death rate. So these two rows, right, these two rows give me opposite results. So that's the paradox. Right? Because it's like, okay, if I look at one, I make one conclusion. If I look at the other one, I make another conclusion. So the question is, which conclusion do I make? And with observational studies, you never want to look at the overall results because there could be a confounder. So here, I would want to look at the individual results, and I would conclude, all right, smoking definitely shortens your life here, right? If you're old or young, doesn't really matter, but on the relevant age group, the smokers have a higher death rate. So these overall results are definitely misleading due to the confounder. So they're telling us non-smokers had a higher overall death rate because most of them, or 26% of them were old. Well, only 8.4% of the smokers were old. So what they saw, why did this happen? If we look at the older people have the higher death rate. Look at these numbers. The smokers, there's only 49 of them that are old, whereas the non-smokers, there's a lot more old people. So because there's a lot more old people, that's making this overall death rate look higher. Okay, does that make sense? So there's mostly, like I said, in the smoker group, there's not a lot of old people. Non-smokers, there's a lot of old people. So that's what's making the overall results different. All right, and then they say if you control for age or stratify based on age, you get the opposite. Smoking shortens your life. So that is what we want to trust for sure. Down here, they're telling us Simpson's paradox, again, is just that the overall percentage is misleading because of the confounder. And once you get rid of the confounder, once you stratify, you see the opposite of the overall results. So that's the idea with Simpson's paradox. And I guess to kind of conclude this part of the notebook, I'm just going to write down a basic idea that we want to come out of with observational studies. So in observational studies, do not compare everyone in treatment to everyone in control. All right, that's the main point, everyone in control. And there's 3 reasons why we shouldn't do this, okay? First of all, the treatment and control groups are going to be different. So we don't want to be comparing apples to oranges. So that's reason number 1. The treatment and control groups are different. Okay? And these differences are called confounders. So the confounders can mix up our results. All right? And then lastly, the most extreme case is that Simpson's paradox can occur. So that's my 3rd reason. I'm going to say sometimes Simpson's paradox can occur. All right, so this, again, sums up that observational studies have problems, right? Randomized controlled experiments, they don't have any of these problems because the treatment and control groups are as alike as possible. So at the end of a randomized controlled experiment, we can make a conclusion and say, all right, either a treatment causes the response or it doesn't. Whereas with observational studies, we need to adjust for confounders before doing anything like that. Any questions on this? All right, let's keep going. So chapter 2 has one more part to it. Okay, and it looks like, there's 2 more pages of chapter 2, and we're just going to talk about, it says, what do you do with people who drop out of a study? This is the last experimental design thing we're going to talk about, and this is a common problem. It says, do you include them or not? Right? Is there a rule? Should I try and find them and track them down? Should I just ignore them? Should I get rid of them from my data? What is the deal? So we're basically going to look at an example of a good experiment. So we're going to look at a randomized controlled experiment where people drop out of the study. So a good experiment gone bad, I guess we can say. And this is number 1. So it's the clofibrate trial. It says this data contains observational data within a randomized controlled experiment. So they want to know, how can we analyze the results to keep the original randomization? So they did everything right in this study. They said, it says a randomized controlled double-blind experiment, good, was done on middle-aged men with heart disease to see if clofibrate, a drug that lowers cholesterol, would prevent heart attacks. So they had this drug, they wanted to test it out, randomly divided their subjects into a treatment and control group, and the treatment group got the clofibrate, control group got a placebo. It was double-blind, they did everything right. They were on the road to making a good conclusion. But it says the patients were followed for 5 years, and then when they looked at the death rates, they realized that not everyone took their medicine. Again, common problem. So what do? It says if you just look at the subjects who took the clofibrate, and we're going to call them adherers, they adhered to the treatment, then their death rate, so let's see, there's this chart. They're saying if we just look at the adherers, the people that took the clofibrate, their death rate was 15% compared to 25% for non-adherers. So they're looking at these 2 numbers. They're saying, let's look at the people who took it, the people who didn't, and it looks like the drug worked, right? Lower death rate for the adherers, higher for the non-adherers. But if you look overall, they're saying the patients were followed 5 years and the death rates were basically the same if you look at the overall results. So overall results, we have clofibrate, 20%, placebo, 21%. So they're about the same. And now they're asking us, it says, which comparison should be used? Should we look at the adherers versus non-adherers? Should we look at everyone in treatment versus everyone in control? Or something else? Is there another comparison that you think would work? What did you guys basically say? You said I should look at this number versus this number, 15% versus 15%, right? People who took the clofibrate, the good people, people who took the placebo, the good people as well, the people that did what they're supposed to do. And that makes sense, right? That's what I thought when I was first looking at this. That seems to make the most sense. But let's think about what happened here. So we have this good experiment. The subjects were randomly divided, all right? They were randomly divided into a treatment group and a control group, all right? And then in the middle of the study, we got this observational data within this random division. So basically the people in both groups decided, are they gonna take their medicine or no? And so they self-divided, which isn't good, right? There's probably reasons why they decided to take their medicine or why they didn't. People who take their medicine versus people who don't are different in a lot of ways, right? Maybe the adherers, the people that did what they were supposed to do, in general, they might be more responsible, healthy people, all right? That's definitely an option. Maybe these non-adherers are the slackers. Okay, so this isn't good. This whole self-dividing into adherers and non-adherers, that's messing up our results, right? But so the answer to this question, what comparison should be used? We want to keep this random division, all right? So it's best, even though we have adherers and non-adherers, it's best to always, if you start off with a good experiment, look at the overall results, okay? So I'll explain this more in a minute, but I'm going to write down the rule. The rule is, in general, all right, in general, we want to compare everyone in treatment, okay, everyone in treatment to everyone in control. And then I'm going to add, this is important, when you have a randomized controlled experiment. Okay. So, why is that the case? Well, what if I did make the comparison that most of you guys said, these two, 15% versus 15%? I get the same result as if I look overall, right? I get that the drug didn't work. I get the same result. So does it really matter? That's the question. And in this example, it doesn't, because we get the same conclusion. But that's not always the case. These two comparisons, this versus this, and this versus this, don't always give you the same conclusion. So we'll look at an example where they do that. But I also want to address this. I just said we want to compare everyone in treatment to everyone in control. So ultimately, I'm going to look at these two numbers if I have a randomized controlled experiment. You might be thinking, I literally just said the opposite over here, right? But this is for observational studies, so they should be opposites, right? Observational studies aren't good. Treatment and control groups are different. So I said never compare everyone in treatment to everyone in control. That's if you start off with a bad experiment. Here, I started off with a good experiment, and I don't want to contaminate it with bias by looking at adherers and non-adherers. Sometimes, sure, in an ideal world, there would be no adherers and non-adherers. Everyone would just do what they're supposed to do. But if this happens, it's common that it does, this is the best way to deal with it. Still just keep them in the data, right? I guess if you think about it, people who are given medicine, some of them might be non-adherers. So we want to keep that original randomization. Down here, number 2, example 2, this is kind of another reason why that comparison is best. It says, what if the data came from a study where it's impossible to have a placebo? So sometimes we don't even know these numbers, all right? Like this one, it says like to see if exercise helped prevent heart attacks, then we wouldn't know who was an adherer or non-adherer in the control group. We'd just see the total. So basically, with this, what we're dealing with is the same thing. We have all these heart patients. They're randomly divided into a treatment group and a control group. Now the treatment's exercise classes, not a drug. Control group is just they don't exercise. And so see how we can't even get adherers and non-adherers? How do we tell if someone didn't exercise or didn't exercise? It doesn't make any sense. So again, this would be the comparison we want to make because the other option isn't even there if we wanted to. And then we can see here in the diagram, divided by choice, again, I'll say it over here, this contaminates our data with bias, the whole divided by choice. Because again, maybe the reason these numbers are different, it looks like the people who chose to exercise, their death rate is 15%. The people who chose not to exercise have a higher death rate. Maybe that's because they're just not responsible people in general. They don't take care of themselves. We don't know if it's because of the exercise classes or other factors because they self-divided. So this again, right here, this is observational data, okay? Observational data within a randomized controlled experiment. Within a randomized experiment, which isn't good. Okay, so one of the reasons that this comparison isn't good, adherers in treatment versus adherers and control is because sometimes we don't have that data. On the next page, we're going to look at an example where we actually get the opposite results of what is really true if we do look at that data. So before we do that, does anyone have any questions? Yeah. I can't hear you. Talk louder. In general, yes, but here they're specifically looking at heart attack patients. So they're trying to figure out, okay, does exercise prevent heart attacks? And, so you're saying, so you're asking, could we say that these people are going to live longer because they're exercising? Yeah, there definitely is. And we know that exercise is good for you and does prevent heart attacks. So yeah, this is... with this one, the main idea is just trying to see that for some things that you can't have a placebo, basically. But yeah, that's a good point. Any other questions? Okay, next page. Now it says, why not compare adherers in treatment to adherers in control? This is a $1 million question. You might still be kind of skeptical of this and be like, is she actually telling the truth? But if we think about, go back to the first day of class, right? What's our main goal? Our main goal, I feel like I've written this a bunch, but our main goal is to have the treatment and control groups as alike as possible. As alike as possible. So on the test, on the exam, if you're ever confused, on the experimental design questions, think about this and it should help you. It says, we need to make sure the groups we compare are nearly identical before the treatment starts, right? This is review. Why do we do randomized clinical trials? We want the groups to be as alike as possible, so at the end, if we see a difference, we can attribute that to the treatment. Adherers and non-adherers, again, they're self-selected, so the reason that they do what they do might be different if they're in the treatment group versus the control group. Okay, for example, if the treatment group is taking a drug and the drug has terrible side effects, maybe that's why people stop adhering. Whereas the control group, they're taking a placebo, if they stopped adhering, it would be a different reason, right? Placebos don't have any side effects. So if we think about it that way, it says these differences can confound our results, making it hard to determine, does the drug actually work? All right? So again, it's like if we look at that observational data, it's like we're changing our randomized controlled experiment into an observational study. We're adding potential confounders. So here's an example of where that happens. All right? This is a completely new example, number 3. It says a randomized controlled double-blind experiment was done to see if offering more challenging bonus problems would improve students' performance in a large intro stats class. So this was a Stat 100 example, actually, that we did. We thought maybe our bonus, like the pre-lectures and the surveys, iClickers, all that stuff, they thought, maybe the bonus is too easy. What if we made the bonus harder? What would happen? Would that help students do better? So what we did, we took half the students, randomly assigned them into the treatment group. They got the hard bonus, and the control group. They just got the regular bonus problems that you guys are getting today. And it says at the end, here are the results. At the end of the semester, the averages, this is what happened. The challenge group did worse. So hence, we got rid of the challenge bonus and just left the original bonus. 80 versus 84%. So the people that had the harder bonus actually did worse. So we determined it wasn't any good. We should just stick with what we have. So we looked at the data and saw this was a problem, right? Not everyone did the bonus problems, okay? Of course, not everyone in the class does 100% of the bonus. And we looked at these adherers versus non-adherers. And what we saw was, here are the results. So again, we took the whole class and we randomly divided them. into treatment and control. All right? And if we look, we're saying if we look at the overall results, it looks like the control group did better. The treatment group did worse. Challenge bonus doesn't work. But we did notice that we had adherers versus non-adherers. And this is, you guys said, well, the best comparison would be adherers in the treatment versus adherers in the control, right? And I get that logic. But look, what do we see here? We see actually the opposite result of what we get overall. On the other page, we get the same result. The drug didn't work. Here, it looks like the adherers in the treatment group did better than the adherers in the control group. So we thought about why that might happen. And what we saw was the reason that people adhered, the challenge bonus, the adherers in the treatment group were the smartest students in the class. They benefited from the challenge bonus, and then the not as smart students just didn't do it. They thought it was too hard. So if we're thinking about Stat 100 overall as a class, we want to know for everybody, right? We can't give some people one thing, other people another. So overall, what's best? And overall, to keep that random division, we got to look at these. So what happened was the standard bonus definitely helped, but only the really, really, really smart people were even doing the challenge bonus. So we decided to get rid of it. So it says, which comparison group should we use? Again, same thing. We want to keep that random division. I'm going to say everyone in treatment versus everyone in control. It's actually, this is very similar to Simpson's paradox, right? Because we're seeing, if we look at different rows, look at overall results or individual results, we're seeing the opposite results. So they're saying down here, it's actually, you can think of it like Simpson's paradox, but for randomized experiments. Overall results can be opposite to subgroups, but we want to keep the original randomization. So bottom line is we don't want to compare groups that were self-divided, ever. Anytime that humans decide something, there could be bias. So just keep the original randomization to get your result. And again, it would be best if we didn't have to deal with this, right? But the question is, when it happens, what do we do? And if you're interested in this idea, and these experiments are called intent to treat. That's just like the formal definition, or formal language, but it's the same kind of idea. If you want to look more into that, feel free to look it up, because they talk about these exact type of examples and why this comparison's best. So that is pretty much it for chapter 2. We're going to move on. We're done with experimental design until exam week when we do a review. There's these summaries at the end of each chapter. I don't go over them in class, but these are really good to help study for the tests as well. So next page, we are actually moving on to a whole new part 2, descriptive statistics. And the first thing we're going to do is talk about histograms. Okay, so we're going to talk about histograms, then we're going to talk about measures of center and spread, and then the last thing we're going to do for exam 1 is talk about the normal distribution. So that is the plan for next week. But let's talk about histograms. So histograms, I'm sure you guys all have seen a histogram before. Here's one right here. This is for NBA salaries in the 2003-2004 season. They also give us on the left a bar graph. Okay, I'm sure everyone here has seen a bar graph before as well. And you'll notice that these two look different, right? They look different, but they're actually showing the same data. All right, so why do they look different? What's the difference between a histogram and a bar graph? And the biggest difference is that with histograms, the x-axis actually means something. The x-axis, I should write this, the x-axis is drawn to scale. Okay, so histograms are good for numeric data that can be represented by numbers, whereas bar graphs are better for categorical data, because if you look at the x-axis here, look at this, 0.25 to 1, 1 to 2, 2 to 5, they're all these bars are the same length, The intervals aren't the same length. So these just represent categories. So you can see on a bar graph, the x-axis is not drawn to scale. All right, so really the only thing that you can look at, the only thing in terms of numbers that you can look at on a bar graph is the height. So here you only look at the height. So the way you'd read this thing, you'd say 0.25 to 1, okay? Well, here's the count. It looks like just over 100, about 120 people had salaries in that range, okay? Whereas a histogram, you look at the areas. You don't just want to look at the height, you want to look at the widths as well. So with the histograms, you look at height and width, whereas the bar graphs, you only look at height. So I'm going to go ahead and say that as well. We look at height and width, the areas. So we can find the area of any of these bars and say, all right, well, 25% of people lie within this interval, or whatever the area is. So that's what we're going to do. We're going to calculate those areas. All right? They told us both graphs depict the same data, but the histogram actually tells us more. The histogram is better for data with numbers. Bar graphs, good for things like eye color, hair color, counts. It just tells you how many people fall into each category. And we don't really focus that much on bar graphs in Stat 100 because we deal with a lot of numbers. So don't worry too much about bar graphs. All this is saying basically what I just said. Again, bar graphs are better for categorical data, which doesn't come up too much in Stat 100. And then what else? Let's see. It says, note that the widths of the blocks in the bar graphs don't mean anything. We already talked about that. Histograms, better for numeric data. Is there anything else that we didn't say? Here it says its area indicates what percentage of players belong to the category. And we'll look at what the height means as well. It says the height indicates the density or how crowded the block is. Okay, last thing, again, you guys can read all this on your own if you want, but this is important. It says in a histogram, the total area of the blocks is 100%. So keep that in mind. This is always the case. Any histogram, that's going to happen. Okay, histograms, got it. What else are we going to do with these histograms? So I want you guys to know how to read them and how to draw them, okay? Of course, in today's day and age, you guys probably aren't going to be drawing histograms very often because you can do it on a computer, but it's important to understand where everything comes from. So let's look at reading them first. It says, below is a histogram representing the final scores of a group of students. Okay, this looks good. Our histogram has most of the data over here, right? Only a little bit over here. Okay, so the final score, that's our variable. That's on the x-axis. It's represented by a number. And then the y-axis measures the density. You can think of it as the percent per point. So all that means is, so the height, right? So like this height, the height of this first block is 0.5. And a lot of times you'll see on histograms, they'll write the height above the block in parentheses, just because sometimes it's hard to tell what it is. But this is 0.5. So this means the percent per point basically means that like 0.5% of people got a 1, 0.5% of people got a 2, 0.5% of people got a 49. So it's like the crowdedness of this interval, I guess you could say. So we're going to look more at that in a minute. But even more important is the area. How do we find the area? Well, this is pretty nice because all these are rectangles. So area of a rectangle, width times height, right? So that's what this chart is asking. It says, what percent of students scored in the following intervals? That's our first question. So 0 to 50, the width here is 50, right? 50 minus 0. 50, and then the height is 0.5. So to get the area, they're saying the percentage is just the area, which for a rectangle is just width times height. So the area is 50 times 0.5, which is 25%. So that means a lot of times also you'll see the percentage written inside the block, but that just means 25% of students got between a 0 and a 50 on the final. Okay? And then go ahead and fill in the rest of these. I'll let you guys do this on your own. Fill in the rest of them for the other intervals. Our next interval is 50 to 60. That's a width of 10. Right? Between 50 and 60, there's 10. And then the heights, this is 1. Next one's 1. This one's 2.5, 2, and 1. So we just want to find the area of all those blocks. So feel free to start. I'll do it up here. Okay, so you should get something like this. So just width times height, super easy, right? And then I guess I should write these, let's see. They like having the percentage inside, so you can easily read it. 25%, 20%, and 10%. That looks good. And remember, the total area, if I add up all these percentages, I should get 100%. And I do. So that's a good way to kind of check yourself before you wreck yourself on the exam. Okay? So that'll make sure that you don't make a mistake. It's easy to make one. But yeah, I'm good. 100%. So now, that's the first question about the histogram. I can answer more questions. Let's do the 0 to 50. 0 to 50 is 25%, and then 70 to 80 is also 25%. So it's equal to this next one, let's see, 80 to 100. Well, we have 80 to 90 and 90 to 100. So 80 to 100 is just 20 plus 10, right, which is 30. So that's 30%. And 0 to 50, we said was 25%. So the percent of people who scored 80 to 100 is actually greater than the percent of people that scored 0 to 50. So if they ask you for like 2 separate intervals, you just add up 80 to 90 and then 90 to 100. Add up those percentages. That works. Next one, let's see, what do we have? What percent of students scored over 50? So I can either look at my chart and say, all right, here's 50, everything greater than that, or I can look at my histogram and say over 50, all right, I'm going to add 10 plus 10 plus 25 plus 20 plus 10, right? Add all those up, you should get 75. Yeah. So I'm going to say 75%. Okay? Any questions on that? All right. What else? It says if you add 10 points to everyone's score, how would the histogram change? So basically, if I took all these people and added 10 points to their score, so now my range would be 10 to 110, right? The person who got 0, now they'd get a 10. Person that got 100, now they get 110. So all I would do is basically shift this histogram 10 points to the right. The shape wouldn't change because I'm doing the same thing to everyone's score. Distribution doesn't change, just the x-axis goes over to the right, goes over 10 points. So I'll say for this one, how would the histogram change? I'll say the shape would stay the same. The shape would stay the same, but the histogram would shift 10 to the right. I guess I'll say would shift 10 points to the right. And then again, you can also say the range would change. The range would be 10 to 110. Still be a range of 100, just shifting it over. So that's what would happen. Same kind of thing if we deducted 10 points from everyone's score. The whole thing would shift, well, that's weird because I'm facing the other way. But this whole thing would shift to the left. That's all that would happen. Okay, last one. It says, what percent of students scored exactly 65? Assume an even distribution throughout the interval. So this question comes up a lot. You'll see it on the practice tests. And it's kind of strange. What percent of students scored exactly 65? So let's look at our histogram. All right, here's 65. All right, I know from looking at this, 10% of students scored between 60 and 70. Okay, so I'm going to draw, that's the interval I'm concerned about. So I'm going to draw it down here just so you guys can see it, but I'm going to make it big. So this is 60. This is 70, and then what was the height? 1. The height was 1. Okay? So they want to know, we know 10% scored within this interval. They want to know, here's 65, what percent of students just got a 65? And they're saying to assume an even distribution throughout the interval. So they want to know, what's the histograms we look at area? What's the area of this little sliver right here? And if it's an even distribution throughout the interval, we can just assume that the width of 65 is just 1, right? The width is 1, and then the height is also 1. So if I wanted to find that area, we know that the area is the width of just one number, you can assume it's just 1, times, and then the height, they're saying, assume that even distribution. So throughout 60 to 70, the height is always 1. So I'd say 1%. What percent of students scored exactly 65? Just 1%, right? I know it has to be less than 10%. 10% of students scored between 60 and 70. Okay, drawing histograms. Next. Let's draw them. It gives us the steps right here, but I don't want to do the steps. I just want to do it. So you guys can read those if you want. But here's the example. It says, table below gives the GPAs for a high school senior class of 500. Fill in the table below and then draw the histogram representing the data. So my variable is GPA. All right? That's the thing that I'm going to get a bunch of GPAs. The thing that changes for everyone. So GPA is going to be on my x-axis. All right, I'm just going to go ahead and write that down here. So this x-axis is the GPA. The y-axis on a histogram is always the density, or the percent per point, right? The height tells you what percent of people scored exactly each number in that interval. So if we fill out this chart, we can easily draw the histogram. It says the intervals include left endpoints, but not right. That's important for answering questions. They have to tell you that. For example, the 2.0 to 2.5 interval contains students who have a 2.0, but not 2.5. So then the next interval would contain the 2.5. It says, note, step 1 has already been done for you. What was step 1? Break the data range into intervals. Yeah, so I'll give you guys the x and y axis if I ask you to draw a histogram on the test. So this would be 0, and then if you go every two blocks, we should get right to 4.0. 3, and then 4. And then for the density, for the percentages, the highest one is 60. So if you just do, again, go every 2 and go by tens, that should work. 10, 20, all the way up to 60. There we go. So that's me giving this to you guys. And we need to figure out, we have 4 intervals. They gave us the intervals. So we're going to have 4 blocks on our histogram. So we know there's 500 students total, right? They told us there's 500 students in the class. And we want to know what percent of students got within each interval. Well, percent, how do I figure that out, right? This is just 50 out of 500. 50 students got between a 0 and a 2.0. So 50 out of 500 we want to change that into a percent. Hopefully everyone's good with that. 50 divided by 500 is 0.1, multiply it by 100 to get 10. So this is 10%. Yes? Pretend it was already there. It's not, but I would give it to you, just because you'll see that's going to be the highest number that we have for the height. For the, height, the last column. Yeah, you guys won't have to come up with that. Okay, next one, 2.0 to 2.5, 150 out of 500 students got a GPA within that interval. 150 divided by 500 is 0.3, which is 30%. And then the next one, 2.5 to 3.5, that's 250 out of 500. So that gives me, that's half, 50%. And then the last one, I know my total area has to be 100%. So what do I have so far? 10 plus 30 plus 50, I have 90%. So this one's got to be 10%, right? Or I could take, again, 50 out of 500 is 10%. Same thing. So I have the area. The widths of the intervals are pretty much given, right? Because they give me the intervals, 0 to 2, that's a width of 2. 2.0 to 2.5, that's a width of 0.5. And then 2.5 to 3.5, that is a width of 1. And then 3.5 to 4.0 is also a width of 0.5. Yes? That is a good question. Here, since 4.0 is the last one, assume it is included in that graph, yes. Only for the last one, though. That's a great question. But like for 2.5, that would be included in this bar, not this one. Okay, and then lastly, we just need to get the height, and then we can draw it. So with the height, they're saying just use the fact that area is equal to width times height. And we have, right, we have the area and the width. So we're just rearranging this equation to solve for height. We're saying height is, right, divide both sides by width, you get area over width. So for the first one, the height is just going to be my area is 10, okay, and my width is 2. So the height is 5. All right, the next one, my area is 30, and my width is 0.5. So I get 60 as the height. That's the tallest height. Next one, I get 50. 50 is my area, divided by height is 1. So that's 50. And then last one, I have 10 divided by 0.5, which is 20. So again, this last column just comes from rearranging that area formula. And now go ahead and draw your histogram. We know 0 to 2.0, that interval has a height of 5. So I'm going to go, here's 5 right here. There's my first block. It has a height of 5 and an area of 10%. Next one, we have, let's see, 2.0 to 2.5. The height is 60. So I'm going to actually go all the way up to the top. Height is 60. And then area is 30%. Okay, and then 2.5 to 3.5, the height is 50. So I'm going to go up to 50. And then the percent, the area is 50%. So 50% of students had a GPA between 2.5 and 3.5. And then the very last one, it looks like the height is 20. 3.5 to 4.0, the height is 20. And then the area is 10%. Okay, that looks good. It says the interval 2.5 to 3.5 has the most people. Is it the tallest? No. Remember, height isn't as significant as area. Area tells you what interval has the most amount of people. Does it have the greatest area? Yes. All right, we're good. So I'll see you guys on Tuesday. Have a good weekend.